My name is Manvi Sinha and I study in Sri Venkateshwara College of Engineering. My USN is 1VE23IS028. My subject name is Data Structures and Applications and its code is BCS304. Today we'll discuss about dynamic hashing and leftist tree. Welcome to this video on data structures. Today we are going to explore the foundational concepts that make programming more efficient, organized, and powerful. So, what exactly are data structures? Think of data structures as the containers or frameworks for organizing and managing data. Whether it's a list of numbers, a collection of names, or even complex connections like social networks, data structures are the key to storing, processing, and retrieving data effectively. So, why do we need data structures? Imagine a library without bookshelves. Without structure, finding a specific book would be chaotic. Similarly, in programming, data structures help us organize and access data quickly. This efficiency is especially crucial when working with large amounts of data, like search engines, social media, or gaming apps. So, there are some common types of data structures, like arrays, linked lists, stacks, queues, trees and graphs, and hash tables. So, what is dynamic hashing? Dynamic hashing is a technique used in database systems and file systems to efficiently handle situations where the size of the data changes frequently. Unlike static hashing, where the hash table size is fixed, dynamic hashing adjusts the hash table size dynamically as more data is added or removed. This flexibility makes it particularly useful for applications that experience unpredictable or high volumes of data, as it reduces the need for rehashing all the data entries every time the table grows or shrinks. So basically, how dynamic hashing works. Buckets and overflow. Initially, data is stored in a fixed number of buckets. When a bucket becomes full, dynamic hashing creates new buckets rather than just relying on overflow areas, which helps maintain performance. Then hash function. Dynamic hashing uses a hash function, just like static hashing, to assign data to specific buckets. However, as the data grows, the hash function is adjusted to accommodate the increasing number of buckets. Splitting and merging. When a bucket reaches its capacity, the system splits it into two, redistributing the data based on an extended hash function. This allows the structure to adapt to new entries without rehashing the entire dataset. If data is removed and space is freed up, the system may merge buckets to optimize storage, reducing unnecessary buckets. So, there are basically two types of dynamic hashing. First one is extendible hashing, which uses a directory to manage pointers to buckets, making it easy to expand the hash table by adding bits to the hash keys. The second one is linear hashing, expands gradually by splitting one bucket at a time, avoiding the need for a directory. It's generally simpler but maybe less flexible than extensible hashing. So, the primary advantages of dynamic hashing includes improved performance in data retrieval, reduced collision rates, and the ability to handle varying data loads. This adaptability makes it suitable for applications with unpredictable data growth. So we'll discuss about efficient use of space. Adjust size according to the number of entries and optimizing storage. Reduced collision means fewer overflow areas means less time spent searching through linked lists or overflow buckets. Adaptability handles large, unpredictable data volumes without the performance drop that static hashing can experience. Dynamic hashing is widely used in scenarios where data can grow and shrink unpredictably, such as database indexing, distributed systems, and dynamic storage environments. So, challenges in dynamic hashing. Dynamic hashing offers flexibility and scalability, but it also brings several challenges, particularly in managing performance and complexity. Here are some of the key challenges in implementing and maintaining dynamic hashing. First one is increased complexity. Dynamic hashing techniques such as extendible and linear hashing are more complex to implement compared to static hashing. Managing bucket splits, merges, and rehashing requires sophisticated logic and additional data structures, such as directories or metadata to keep track of changes. Second one is performance overhead. While dynamic hashing is designed to handle large and variable data, it introduces some performance overhead due to frequent splits and merges. Each time a bucket is split or merged, there is a computational cost involved, which can slow down data access during these operations. Third one is memory management. Dynamic hashing requires additional memory to maintain directories or to store overflow information. This can lead to memory efficiencies, especially in systems with limited memory resources. Additionally, memory fragmentation may occur due to frequent bucket splits and merges. Fourth one is handling concurrent access. In environments where multiple users or processes access the hash table simultaneously, concurrency control is challenging. Splitting or merging buckets during a read or write operation requires locking mechanism to ensure data consistency, potentially leading to delays or bottlenecks. Fifth and the last one is load balancing and distribution. Dynamic hashing aims to keep data well distributed across buckets, but achieving this balance is challenging, especially with highly skewed data, where some data is accessed more frequently or concentrated in specific buckets. Poor distribution can lead to hotspots, with certain buckets being overloaded, affecting retrieval speed. Addressing these challenges often involves trade-offs between performance, memory usage, and implementation complexity, which makes choosing the right dynamic hashing approach crucial for specific applications. Leftist trees. A leftist tree is a type of binary tree used to implement priority queues efficiently. It is structured to make operations like merging two trees quick, which makes it particularly useful for applications that require frequent merging of priority queues. Leftist trees are a type of priority queue that maintains a balance between tree height and node distribution. They are particularly useful for implementing efficient mergeable heaps, providing optimal performance for certain data operations. So some of the key characteristics of leftist tree include min-heap property. A leftist tree follows the min-heap property, meaning the value at each node is less than or equal to the value of its children. Second one is NPL, null path length. The null path length of a node is the shortest distance from that node to a leaf. The third one is skewed structure. To maintain the leftist property, leftist trees tend to be skewed to the left, with the right paths being shorter than the left. So why leftist trees? The leftist structure helps make merging true leftist trees efficient, typically 0 time, where n is the number of nodes in the tree. This is much faster than merging two standard binary heaps, which usually requires a complete rebuild. Advantages of leftist trees. The key benefits of leftist trees include their ability to support efficient merge operations and maintain a low height, which ensures quick access to the minimum element. These properties make them ideal for applications requiring frequent merging of datasets. So there are some of the operations that are performed on leftist trees. First one is merging. The merge operation is the fundamental operation in leftist trees. When two leftist trees are merged, the tree with the smallest root becomes the new root, and the two right subtrees are merged recursively. After merging, the tree is adjusted to ensure the leftist property holds. The second one is insertion. Insertion in a leftist tree is done by creating a new node and merging it with the existing tree. This keeps insertion time efficient as it only depends on the merging time, which is 0 log n. Third one is deletion of minimum element. Since the minimum element is always at the root due to the min-heap property, deleting it involves removing the root and merging its left and right subtrees. This operation also takes 0 log n time. When leftist trees offer significant advantages, they can be complex to implement. Maintaining the leftist property during insertion and deletion operations requires careful management, which can pose challenges for developers. Applications of dynamic hashing. Dynamic hashing is widely used in database, caching systems, and data retrieval applications, where performance is critical. Its ability to adapt to changing data loads makes it a preferred choice for many software engineers. Applications of leftist trees. Leftist trees are more often utilized in algorithms that require efficient merging of sorted lists, such as Dikshatra's algorithm for shortest paths. Their unique properties make them suitable for various computational problems. So, first we will discuss about example of leftist tree usage. Leftist trees are particularly useful in applications where merging of priority queues is frequent, such as in efficient driven simulations, where events need to be processed in specific order, but events can be dynamically added. Network optimization, where algorithms may require frequent merging of priority queues to handle dynamically challenging properties or paths. So now let's move on to the conclusion and future directions. In conclusion, both dynamic hashing and leftist trees offer unique advantages for optimizing data structures. Future research may focus on improving their performance and exploring new applications in emerging technologies like big data and machine learning. Thank you for joining me on this video.